Before we start the next session, just Slido. I can see we're asking questions and it's great, very useful. There is also one more thing that I wasn't good enough to actually let you know, that there are those polls at the end of the sessions that you can rate the speakers. So please take some time to just rate it and maybe put some comments. That'd be really appreciated. Mm-hmm. Okay, so our next session is with Marcin Szeliga, who specializes in Microsoft technologies, as I understand, right, as an ML practitioner.
Yep.
And as I understand from the abstract, at least, you're going to be talking about AI replacing ML engineers, right?
Very good introduction.
More or less.
Okay, so
yeah?
yes,
okay,
yes.
so we'll see.
So let me start with this quote or this meme. So Igor Korolev, data scientist at Roche, said that data scientists won't be replaced by automated machine learning. Nevertheless, those who use AutoML will replace those who don't. And the goal, the topic of this session is to check what he actually meant by saying that. Okay? So, as you already noticed, I'm Marcin Szeliga. I'm independent consultant working with Microsoft Data Platform for over 20 years. I saw it growing and had some time to write about it. You might have seen that book. It was quite popular. Hopefully you haven't seen that one, as it's not published yet. But it will be this year. And that's my email address. You are more than welcome to stay in touch with me. So, machine learning has become a vital part in many aspects of our daily life, and it's becoming more and more important. Still, many machine learning methods is very sensitive to plethora of designing decisions. So with this, building a machine learning applications or machine learning systems requires highly specialized data scientists or domain experts. Otherwise, the performance will be not good enough. So it's turned out that machine learning, a field dedicated to build systems that automatically learn from data, heavily depends on human experts. Did you find this ironic or not? That's the first part. And as you know, let me go back here. As you know, a machine learning experiment is basically a loop of trial, errors, and improvements till you get to the point where the performance is good enough. And it can be divided into 5 major steps. The first one, data preprocessing or feature engineering. It's said that about 80% of any machine learning project, time and budget, is consumed by this step, data preparation step. And this step is also the most creative one. It includes not only data cleaning, but also transforming aggregations and or adding some features. Then the selection of machine learning algorithms is somehow easier, as this step depends on ML task given, and data. The third one is hyperparameter tuning or hyperparameter optimization. So hyperparameters are parameters that define the model architecture. Thus, the searching for the ideal model architecture is referred to as hyperparameter tuning. Those hyperparameters can address model architecture questions strictly, like how many trees should I grow, or what's the required minimum number of examples at leaf level, or the learning procedure optimization. For example, what's the best learning ratio? And you are going to build many models to solve a single ML task. Training is just applying configured model to training examples, nothing more. So we ended up with many models. We have to compare the performance of those models. That's the last step. Nothing new, probably, for most of you. So let's compare this approach with that one. So what's the goal of automated machine learning? Actually, it aims to reduce the demand for data scientists and by enabling end user or domain experts to build those machine learning models automatically and by themselves. Okay? And it looks like this. So, by the way, automated machine learning is nothing new. The key story started over 30 years ago, and many AutoML frameworks matured during this time. Probably the first one was Auto-WEKA, then was auto-sklearn or AutoNet. All those frameworks or those libraries concentrate on solving one problem: how to automatically find machine learning algorithm and sets its hyperparameters. Some other libraries, like feature tools, concentrate on feature engineering part. And as I was introduced as a Microsoft guy, I'm not an employee, by the way, of Microsoft. I'm going to show you Azure Machine Learning Service, AutoML framework that combines both functionalities and adds some more. So go back to this slide. AutoML is all about implementing this kind of scenario. So end user have to provide historical data, set some targets in terms of model performance, like I would like to achieve accuracy 99%, whatever, and set some constraints in terms of number of candidates models or total learning time, whatever. Based on those inputs, AutoML system will build, train, and evaluate machine learning models. So it's like that. And if you think about this, with this in mind, AutoML systems actually promise to fulfill the previous requirement and enable us to build applications that truly automatically learn from data. Yeah, so what about tools? Azure Machine Learning Service, or AML, provides a cloud-based environment you can use to build, train, and evaluate and deploy your machine learning models by auto-scaling CPU or GPU clusters. And in my opinion, it's suitable for all users. It provides from no code to code first experience. Right now, most machine learning is happening in Python. So AML allows you to work with any Python modules of your choice. It's up to you. Or you can use the SDK, because core functionalities of the service are exposed through Python API. You can install this API, a simple pip install command, and you can use it locally. Still, Azure subscription will be needed to fully leverage this SDK. And as you can see here, its aim of the service is to automate all steps of these experiments, from data preparation, feature engineering, through model building, training, evaluation, and deployment. One more term is needed to explain the concept. This is machine learning pipeline, or ML pipeline. An ML pipeline is used to help is used to help automate machine learning workflow. It starts with data preparation, goes through building, training models, and ends at deployment. Nevertheless, the term pipeline is misleading, as it suggests a one-way flow of data. You know that machine learning experiments and ML pipelines as well are cyclic and iterative, as each step, like this normalization, validation, whatever, is being constantly repeated to improve the pipeline performance. Okay? What's important that all those steps actually have to be completed in order to evaluate the whole ML pipeline. Okay. So, Azure Machine Learning Service, quick introduction. It starts with environment setup, so as you can see, all those steps are covered by this service. With this, you have to create a workspace. A workspace is just a logical container that will to store all your experiments. And experiments will, a part of experiment is actually a model or models, mostly, quite often more than one. The environment or workspace creation is quite easy. You can do this via code or using graphical interface. It's up to you. Then there is a data preparation. As I said, 80% of typical machine learning experiments or projects are happening here. And this part is actually hard to automate still. We are making some progress. The state-of-the-art method, deep feature synthesis, was convinced at MIT in 2014. And this deep feature synthesis is not part of AML service, by the way. But still, there is a Azure ML.data prep package, and it contains a lot of method to help you with data assessment and preparation, like fuzzy grouping, automatic file type detection, automatic joining, missing values imputation, and so on and so forth. Then there is the fun part, building models. With Azure Machine, with AML, you can build your models using existing Linux VMs or Spark clusters, if you are happening to use Azure before. You can also provide dedicated compute resources, or as I said, you can use your whole local PCs. But training relatively small models on local computers or single computers is probably fine. More sophisticated models will need more powerful, quite often cloud-based clusters, compute resources. And you can use any Python library of your choice to build those models. In addition, there is the Azure ML.train.hyperdrive package, which will help you to automatically recommend the best pipelines, ML pipelines, for your data set. The train model can be registered under this workspace. Register models, you search for them, tag them, version them, and finally deploy them to containers. So in Azure, there are two options. Azure Container Instances for dev test scenarios, or Azure Kubernetes Service for production-ready deployment. Probably at the end of my, I will talk a little bit more about this AKS, because they have some specific functionalities regarding the monitoring of deployed models. If you wish, IoT edge deployment to FPGA is also supported. So it looks like this service covers end-to-end ML pipeline. That was the goal of this slide. So let's suppose that we have a problem to solve. The credit risk assessment. The data is already downloaded in terms of huge CSV file. Sorry, but it's almost readable, yeah? So that's my experiment name, loans. I just have to select it, compute resources. In this case, it's a cluster. Then provide the training data. Already got some information about this data in terms of statistics and histograms. And as you can see, after specifying task, ML task, in this case, classification. And my target is this is-bad column, yeah, or variable. I already capable or able to launch the experiment. Still, if you want, you're perfectly fine to set some budget, let's say, in terms of number of training candidate models or total training time. That's important because you are going to pay for this. Or customize validation procedure. Also, I will be talking about this validation procedure soon. Or maybe blacklist some algorithm. For whatever reason, I don't want to check this KNN for this specific task. It's up to me. So let's suppose that I just right now launch this experiment. It was all what was needed, yeah? Nothing more, nothing less. And while it's running, we will discuss some technical technical details. What's going on? So, first, we should start with automated data preparation. As I mentioned, this step is the most creative one, and probably for this specific reason, is the hardest one to be automated. Still, because for sure you have to, or at least you should, assess your data before launching this experiment. Maybe select some variables that should be used for features. I don't know. You can use any Python modules for this, or this AutoML.dataprep package I mentioned briefly before with all those fancy functionalities like automatic data scaling or aggregations, or even some domain-specific transformations like datetime variables. Datetime variables by themselves are quite useless in respect of machine learning experiments, but they contain a lot of very valuable information, like day of the week or month, whatever else. So all these important features are extracted for you automatically, and so on. So turning on automated data preprocessing means all those things will happen for you and more. So now we have features. Historically, the first task of AutoML systems were to select a machine learning algorithm that is suitable for this specific task and sets its hyperparameters. To be more precise, our tasks is for given data set. So the data preprocessing step is already done. So for a given data set, simultaneously find hyperparameter, machine learning algorithm, and its hyperparameters. So this combined algorithm selection and hyperparameter optimization, cache optimization, was the very first task that can be automated, and actually most of AutoML frameworks are pretty good at this part of automating ML pipelines. I'm saying this because it may seem easy, but there are some important challenges, hard challenges to be solved. The first one, that the configuration space is complex. It contains mix of continuous and categorical hyperparameters, and it's highly dimensional. The second challenge is the configuration space can contain conditionality. For example, one hyperparameter is valid only if other hyperparameter or combination of hyperparameters take on specific value. The last problem, last but not least, is that there is no gradient function, there is no gradient of loss function in respect to hyperparameters, which means that evaluation of this loss function can be extremely expensive. Probably you noticed that the problem of selecting machine learning algorithm is treated as in that way that the machine learning algorithm is just one more hyperparameter, categorical one. Okay, so by taking this approach, we defined cache problem. Okay. So how to solve this problem? There are different approaches. The first one is solving cache problem with grid search. Grid search is just a fancy name for brute force approach. So with this very basic hyperparameter tuning method, each possible combination of all those hyperparameters values are taken into account. So we are building models for each possible combination, evaluate those models, and the best model is selected. Categorical hyperparameters are taken as they are. All those numerical or continuous are discretized into k equidistance values. By doing this, we can get a finite configuration space to be searched. Easy to implement, easy to parallelization, but this method suffers from the curse of dimensionality, as the required number of loss function evaluation grows exponentially with the dimensionality of configuration space. And this conditionality, so the hierarchical structure of hyperparameters, is not taken into account. That leads to redundant configuration. So we are wasting our time and resources. For those reasons, grid search is not being used in practice, actually. Instead, we can just sample at random some configurations, and by doing this, we already implemented the second method, random search. Okay? That works better, especially if some hyperparameters are way more important for ML pipeline configuration than others. Also easy to implement and parallelization. Still, this cache optimization problem, can be treated as a regression problem. And in Bayesian optimization, the goal is to minimize loss as a model of hyperparameters. The loss is typically root mean square loss function. And a regression model, typically Bayesian typically Gaussian process, and acquisition functions are used to iteratively decide which configuration should be, which pipeline, ML pipeline, should be evaluated next. Bayesian optimization procedure proved to be very effective in practice. Still, this method suffers in high-dimensional configuration spaces, where performance of this method is comparable to random search. So we are almost there. Still, some improvements are needed. And the problem with Bayesian optimization is that those ML frameworks, ML systems, start to build pipelines from scratch each and every time. Meta-learning is actually a way to solve this problem. Meta-learning is the science of learning how machine learning algorithms learn, which means that based on previously seen configurations, we are going to build a meta model that will predict or recommend good performing configurations. Okay? Yeah, and that introduced the computation overhead. We have to fit this model, we have to ask for probably good configurations, but this overhead, but the probability of evaluating badly performing pipelines can be lowered significantly using this approach. And as the actual cost function quite often is very expensive, by using this approach, we can shorten time span needed to find good ML pipelines or good model for given data set. Still, how to do this? And if you think about this Bayesian optimization and the drawback that those ML frameworks starts from scratch, you may find that the problem of predicting the performance of this given configuration, so pipeline, can be cast as collaborative filtering problem. Which means that we can collect some metadata about previous experiments, like some statistics about datasets, some information about task by itself, measurable properties. In addition, the pipeline configuration, of course. Yeah? And based on this historical observation, we can build a meta model that will predict, or at least will give us some ideas where to find well-performing configurations for new unseen ML tasks. This kind of collaborative filtering problem can be solved using probabilistic matrix factorization. This approach is used in ML, Azure Machine Learning service, as you probably already figured out. So the very last part is here. Microsoft Research built a system by putting different ML pipelines in latent dimensions, in latent space. Here you can see first two dimensions of this latent space, where all those ML pipelines are situated based on their performance on specific datasets. Here, ML open datasets were used. Maybe you know, ML open the organization has a massive collection of datasets. So The point is that some regions are way more promising than others, yeah? Based on the pipeline performance. So with this, if we combine this approach with the Bayesian optimization, we will get a system that can search through this enormous configuration space intelligently and efficiently. And that's how Azure Machine Learning service actually works. There are also some minor improvements, performance improvements. The first one is as many AutoML frameworks, AML as well, use k-fold cross-validation to actually evaluate those candidate models. I am assuming you know how k-fold cross-validation works. The procedure is repeated key times. That's the point of this of this point, which means that after evaluating the first fold, if the result is significantly lower than expected, we can abort the learning. Okay? So that's the first performance improvement. The second, ensemble models. Ensemble models also are quite commonly used because they tend to be high-performing ones. It's all about combining different models to make a final prediction. Here, you will get this ensemble learning for free. I mean, with no extra costs, because AML already built and evaluate given number of ML pipeline configurations. Yeah? So we already built like 50 models. So instead of yielding only the best performing configuration, you will get as the very last candidate model an ensemble built on set of the best performing configuration. Okay, so with this, as you can see, I click launched, and the cluster is being provisioning here for me. The warning here means that I will get only 3 nodes. I asked for 8, but there was a quota at that time. Okay. And during the experiment is still running, I'm already seeing some gathering information about this experiment. Like the very first configuration was already perfect one, 100% accuracy. The second also perfect. The third much worse. Yeah, and here are pipelines configurations. The status 3 are running because I got 3 nodes in my cluster, if you remember. Some are still queued, some completed. You can download the model, as you can see, or as I said, you can register it. If you click on the specific model, specific pipeline, you will get a set of metrics, charts, all this fancy stuff. Nice one, good. So the documentation is done for you automatically. And 2 things I'm going to mention briefly. AML, so Azure Machine Learning, is not only about solving cache problem. There is the huge part about deployment, monitoring, deployment and monitoring. Okay? So we discuss only this part, actually, of the service. This can and actually is also automated. So all those artifacts can be created for you, and deployment is one-click deployment. You can even monitor the usage of the model. And the second, in my opinion, very interesting point is here, explainable AI. Because right now it looks like AutoML are even worse black boxes than standard machine learning models. Now nobody knows even what algorithm was used, if you are not interested in this, yeah? So there are Azure ML explain model and Azure ML train, AutoML explainer packages. And they are local and global explainers. Using state-of-the-art algorithm, you can get explanations for all your data, how it works, or for specific example, why I'm not going to get my loan, yeah? Because something is wrong with those variables. In terms of variables, actually, so that's my almost last slide, yeah? Maybe you noticed that I changed the data set. Now we are talking about Titanic data sets. And I just uploaded the Titanic CSV downloaded from Kaggle website. So no data preparation, nothing at all. And I got pretty good, actually, results. I will be in the top 1% with this on Kaggle. And this is also nice. So the most important feature tends to be a part of the name, because name was transformed. Yeah? So there was hash encoding and some more advanced transformations. So all those variables actually tends to be useful as they were. No manual data preparation. And with this, it's time to recap and maybe answer some questions. My point was to demonstrate an AutoML framework. I'm working with this one, but there are many others as well available. And in my opinion, actually, it's a huge thing, because with AutoML, we are building a system that truly automatically learns from data. So there is no more fancy decisions, should I extract this feature or not. It's all based on those techniques I was able to hopefully explain from end to end, from data to explainable AI. Okay, so let me check if there are any questions there. The first one, is Azure ML using generic algorithms in order to be grid search? So actually, hopefully I explained this, answered this question already. So it's not just grid search, it's not just a random search, it's a combination of Bayesian optimization and collaborative filtering techniques, okay? The second one, how does it differ from hyperopt? What is under the hood? It's more or less similar question, yeah? So maybe the first answer is suitable for both questions.
Or maybe this one works. Yeah, so I guess it just shows the problem with Slido a bit, because when you ask the question before the ends, then
it's a great question.
But it's a good question then, yeah, exactly, because it got answered anyhow. So, all right. Anyone, any more questions? Like live questions? No? All right. Okay, so thank you very much.
Thank you.
Thank you.